So looking at net torque, we saw the fact that net torque is the sum of all of the individual torques acting on an object due to the applied forces acting on it. We also looked at the fact that torque is the rotational equivalent of force. So we are going to actually apply Newton's laws to an extent to what's going on here. So we saw right here the fact that angular acceleration was equal to the torque divided by this quantity. So we haven't figured out quite yet what this quantity is, but we are going to end up talking about it. And we're going to end up discussing the bearing that it has. So for now, we're going to go ahead and look at an example. So when you are looking at trying to raise the anchor on a ship, you use what's called a capstan. And there's this lovely thing about a capstan is you get to, because you're applying your force much farther away from the axis of rotation, you are able to apply much less force in order to get that anchor up. So we're given some information, the fact that we are applying our force 7 times as far from the axis of rotation than the anchor is applying its force on that wheel. We know that the anchor is going to weigh 1,500 newtons, right? And it's going to apply a tension of that amount to our thing that's rotating, that capstan. And we're looking at what that sailor is doing, pushing 7 times out. And we want to know what's the force that the sailor is going to put if we look at the net torque being 0. That means our angular acceleration is 0. He's going to move around that circle, that capstan, at a constant rate. So I've drawn a free body diagram, so to speak, of what this is. We already established the fact that counterclockwise rotation is positive. So I have this force, this tension here, that's for my anchor, and where it's being applied. That's the radius for that tension. And then I have the force being applied by my sailor and the radius for that particular force. So that's the diagram that I have going on for this particular case. We are looking at the fact that the sum of torques is equal to I, which we haven't talked about yet, but it's that mr squared times alpha. Because we are looking at the fact that this is going to be moving at a constant rate, right? Our net torque is going to be 0. The right-hand side is going to turn to 0 because our acceleration is 0. So we don't really care what I is just yet. All right. So what's going on here is we're summing in the individual torque. So this is the torque applied by my tension. It's going to cause positive rotation because if I pull this, it's going to move in this counterclockwise fashion. So this is positive. Whereas the force from my sailor is going to cause it to rotate in this clockwise manner, making this term negative. We are able to look at the sine of the angle, but in both cases, we are applying the force perpendicular to the radius or the radial arm so that that angle is 90. Like I said, we're moving at a constant speed. Our angular acceleration is 0. So we can then continue to move on the fact that the radius that is the tension is applying is r, that was given to us in the diagram that came with our problem, and the distance, or the r for which the force is being applied, is 7r. All right. We can again continue so we're going to substitute these quantities in here, and we know sine of 90 is going to go to 1. So my tension times r, so its radius, I remember sine of 90 is 1, minus the force applied times its radius, which is our 7r, is now equal to 0. Because remember, our angular acceleration is 0, so this whole term goes away. All right. So we're looking for force, so we end up rearranging our equation. We know that TR is going to equal F times 7R, and F is going to equal TR divided by 7R. Well, we have R's in both the top and the bottom, so our force is going to be 1/7 that of the tension. We were given the tension in this particular case was 1,500 newtons. 1,500 newtons divided by 7 tells us that our sailor only needs to apply 214 newtons of force. All right. Now we can start talking about the fact that this law, we are going to more formalize it into Newton's second law for rotational motion. It does apply. So we can apply individual forces on a mass at different points on an object, and we can find the torque that is being exhibited on each particle in a non-uniform mass, or even a uniform mass, about its rotational object. The important thing to note is because we're looking at rigid bodies, the whole object is going to move together. Every point on that object is not only going to have the same angular velocity, but also angular acceleration, because they're going to rotate together. Right. So then we're continuing to sort of flesh this out. We're looking at the torque applied to each particle. So we're looking at the torque for 1, right? It's that force of 1 on the mass times the radius times the angular acceleration that it's going to move with, all right? And for 2 and 3. Remember, net torque is the sum of each of the individual torques. All right, so we add all of those up, and because they're moving all together, we're able to then take that angular acceleration from each term and bring it to the front. Well, now we have m1 r1 squared plus m2 r2 squared plus m3 r3 squared. Well, we can simplify that down very significantly to summation notation. All right, we're adding the mass of at a particular point times the location of that particular point from the rotation axis squared, right? And that's what this sort of notation looks like, or talks about. I've sort of already gone through that, but I will tell you that this actually boils down to something. It boils specifically down to the moment of inertia. We do talk about the moment of inertia as capital I. Inertia, remember, is the property of an object or a material or an object to continue in its current state of motion. It either wants to stay still or keep moving at a constant speed. And linearly speaking, the more mass an object has, the more inertia it has. Well, that's certainly true with our rotating objects, but not only does the mass of that object matter, but how that mass is distributed. Stuff very, very close to this axis of rotation is not going to affect its rotation as much as stuff that's very far away from the axis of rotation. So we are looking at that. The moment of inertia is not just measured in kilograms, right? Because we're not just interested in the mass, but its location. So we are looking at the fact that the moment of inertia is kilograms times meters squared. Right? And it does depend on the axis of rotation. Spinning something about its interior radius is very different than about its side. And I will show you a chart for a moment of inertia and what that looks like in just a moment. We are able to then sort of take that angular acceleration, net torque, and sort of rearrange it a little bit so that m times r squared that was in the bottom is now I. Now mr squared is a very generic version of the moment of inertia. It can be simplified or changed a little bit depending on an object's shape. All right, we talked a little bit about this in lab. I've already sort of touched on this. This is able for you to look at stuff very far from the center. It's going to be much harder to rotate than stuff concentrated at the center. So this particular case is a larger moment of inertia, so it's going to be harder to get rotating, whereas this one has a much smaller moment of inertia, much easier to get rotating. So we're going to look at a particular example where we are creating an abstract sculpture that consists of 3 heavy spheres attached by very lightweight rods, right? And they each have a length of 10 centimeters, and they all form right angles together. We are given the masses of each little ball, each of the spheres. We want to know the moment of inertia depending upon which axis it's rotated. Right? In this particular case, we're rotating this whole shape about this axis, whereas this one we're rotating about this axis that's coming out of the paper. And you might be wondering, what on earth does that look like? Well, as a part of the solution on the next page, I've gone ahead to sort of animated that so you can see. So if I look at this page, it's a little odd, but we have this axis here. This whole thing is going to swing out towards you, all right, and rotate so that it's like an elbow, all right. Whereas this one over here is going to be a little bit different. Again, this didn't quite animate, but it's going to swing around this to get that. So these are the two solutions depending on what it was going on. So we found the mass of each object and the distance from the axis of rotation for each of these, and then using the MR squared version of because this is true for a point mass moment of inertia, we were able to find the moment of inertia for each object and then add them together. So this first object is on the axis of rotation since we're rotating this whole object about this point, so it doesn't contribute to the moment of inertia. This mass 2, this 1.5, is going to be this length of the rod away. So we're able to get that and that moment of inertia. And then this one is, again, this rod length away from that particular axis of rotation. So we found the moment of inertia for each, added them up, and that gave us a total moment of inertia for this one. Right? We did the same thing for axis B, where the whole thing is going to spin around the circle. Again, the first one's on the axis of rotation. The second one is not on the axis of rotation. It's still at 10 centimeters away. But now, since instead of rotating about a line that goes through here, we now are going to connect it through the axis that's going through this point, and we see a much different sort of length here. Right? This number actually came from using the Pythagorean theorem. We were told that this rod is perpendicular to this rod, and they were each 10 centimeters long. Because of that, we were able to come up with this number using the Pythagorean theorem. Right? Again, moment of inertia using that sort of equation for the point mass for each one, and then adding and getting a total. So we are seeing that this one, since our mass is a little bit more concentrated towards the center, our axis of rotation, we're seeing a little bit smaller moment of inertia than we are for this one. We have this is a little bit farther away from that center. That brings us to this last thing. This is the moment of inertia for some common shapes. I do have a copy of this for you to use while you are in class. If you're not in class, you can pull one off the internet. So we are looking at a thin rod. So if I were to talk about the moment of inertia of perhaps a meter stick, this is if I were to take that meter stick and rotate it about the 50 centimeter mark, right? Whereas this one rotated about the end, this is where I would hold one end of my meter stick in my hand and sort of wave it around. Right. This is if I were to take a book about its center, a book about its end, and we've looked at these four shapes. All right. This is the cylinder or disc is very similar to the can of soup we dealt with. The cylindrical hoop was the slinky. The solid sphere was like my baseball, and again, the spherical shell is like the tennis ball. All of these are done about its center or diameter, like they were being rolled down a surface. All right. So we're going to be touching on these and working on these and going on.